So, good morning and welcome everybody. It's my great pleasure today to introduce to you Beth Friedman. Beth got her BA in chemistry at Carleton College, which is just outside of Canada. Southern Twin Cities, if I'm not mistaken. And from there, she went to University of Washington, where she worked with Joel Sornton and Cisco, largely looking at ice particle and cloud droplet formation from soot and other particles. She then went to CSU and is currently still there as a postdoc in Delphine Farmer's lab. Among other things there, she's been looking at some alpha-pinene, beta-pinene chemistry and chambers, also looking at diesel fuel emissions and their ability to form particles. And I need to read the title. So the title of her talk today is The Role of Secondary Chemistry in Atmospheric Oxidation Systems, Anthropogenic Perturbations, and Gas Particle Interactions. Okay. Beth.
Make sure this is on. Okay. Can everyone hear me? Okay. Thank you. That was a great introduction because I was going to briefly mention that I am currently a postdoc just up the road at Colorado State University, studying mainly gas phase, biogenic oxidation systems, but also I'm going to talk a little bit about my work with anthropogenic emissions as well. And I did my graduate work mainly looking at particles, and so my current research is really kind of a combination of what I did in grad school, which is really focusing on particles and then putting that together with my current gas phase research. And this work is largely motivated by the fact that primary emissions don't explain the total aerosol growth in the atmosphere. And this was really highlighted by Robinson et al. In 2007, when they did a smog chamber experiment. They put diesel exhaust in there and they oxidized the diesel exhaust. And they found that the total aerosol growth could not be explained by just the primary organic aerosol emissions as well as the known secondary organic aerosol precursors, and that the secondary organic aerosol, or SOA, formed from low volatility gas phase species corresponded to the growth of the oxidized organic aerosol. And if we take a step back and think about the evolution of emissions in the atmosphere, this is again a simplified picture of the evolution of emissions in the atmosphere. So we have primary gases and particles that are emitted from both biogenic, such as trees, and anthropogenic, such as cars and trucks, sources. And these primary gases and particles are quickly oxidized in the atmosphere by the OH radical, by the hydroxyl radical, by ozone, by NO3, to form secondary gases and particles. And then these secondary gases and particles in the atmosphere further interact with each other with further oxidation, and along this kind of at the end of their road, their fate is eventually these gas phase species can functionalize and they can form, they can contribute to the aerosol phase, or eventually they can fragment in order to form carbon dioxide or carbon monoxide. And the fate of these compounds as aerosol or CO2 has implications for human health. We breathe in these particles, as well as cloud aerosol interactions. Many aerosol particles can contribute to or can act as cloud condensation nuclei. And then also, these secondary species can contribute to photochemical smog and thus air quality. And so my research has mainly focused on kind of these secondary species, kind of after these primary species are emitted, what happens, and kind of all these multi-generational oxidation products that form these secondary gases and particles. And again, a lot of what I've been thinking about are the interactions between the gas phase and the particle phase. And it's really these interactions that then inform how the resulting aerosol can then impact human health, clouds, or climate. And I also should point out that I'm completely neglecting deposition in this scheme, which is another important kind of sink of gases and aerosols in the atmosphere. So I'm mainly focusing on kind of the functionalization and the fragmentation of species in the atmosphere. However, the secondary chemistry of even one volatile organic compound from whatever source, either biogenic or anthropogenic, is very complex, and there are thousands that do exist in the atmosphere. And I'm showing, the point of this is not to read it. This is Alphapining, and just a few of its myriad of oxidation products by the hydroxyl radical. So we see, when we oxidize alphapining in a chamber in the atmosphere, we see a bunch of stuff. And it's a very complex system, and that's just alphapining. And there are thousands of VOCs in the atmosphere. And so when I look at this, and what I've been thinking about, what I continue to think about is, can we measure all of these secondary species? And the answer, of course, is no, we can't measure everything. We can try, and we have tried, but we definitely cannot measure everything. And so what do we need to measure of these compounds in order to condense kind of our available information into something meaningful, to further extend this mechanism, which is quite beautiful on its own, but how can then we take that, extend it to other compounds in the atmosphere, other VOCs, other even anthropogenic VOCs, and extend that into then following that regional models, global models, etc. And so I'm going to tell you today about two different examples of looking at secondary chemistry in the atmosphere. And first I'm going to focus on a biogenic system, again, a rather simplified system where I'm only looking at two particular biogenic VOCs in the atmosphere. And so again, we have primary biogenic VOCs emitted from trees, in this case alpha-pinene and beta-pinene. These emissions are quickly oxidized. In this case, I'm just simplifying everything, and we're only going to look at OH oxidation. So we get secondary gases, and then along their way, and they interact with each other in further oxidation, and they either functionalize to be able to contribute to the particle phase, or they could fragment eventually on their way to CO2 and CO. And with this study, what I'm going to talk about is how the bulk gas phase oxidation chemistry, so how these secondary species were impacted by an anthropogenic perturbation, which in this case of sulfur dioxide. And then I'm going to switch gears later in the talk and talk about an anthropogenic, more complex system where we looked at both the gas and the particle phase of emissions and how those change with increasing oxidation of diesel engine exhaust. And so again, we have our primary gases and particles, this time from an anthropogenic emission source. We oxidize them, we form our secondary species along their way to their eventual fates. And in this case, in what I'm going to talk about first, the perturbation was SO2. In this case, we're treating kind of the oxidation timescale and more increasing amounts of oxidation as our perturbation. And again, we're really looking at, sorry about that, about the vapor, the gas and particle interactions. And so again, I want to kind of take a quick step back and kind of talk about why we should even study these oxidation systems and in the laboratory. Our approach has been to be in the laboratory and kind of start with simple systems and build up in complexity in order to understand the oxidation products and what happens in both the gas and particle phases. The overarching goal has been to improve our understanding of how gas-particle interactions impact the total aerosol mass in the atmosphere. And so we have kind of this we have kind of information on the more molecular level, on the more mechanistic level, but then how do we extend that to gas-to-particle interactions, and then how do we further condense that data into parameters that are useful for models that can either, whether they're global models or more regional models, or something that can help tell us we have this mixture of gas phase species in the atmosphere, what does that mean for organic aerosol? What is that? And then down the road, what does that mean for cloud formation in the atmosphere, or what we're going to breathe in, et cetera. And so again, I want to start by telling you about how the bulk gas phase oxidation chemistry changes with anthropogenic perturbations. And this research was really motivated by the fact that anthropogenic and biogenic emissions coexist regionally. And so we have in emissions of SO2, sulfur dioxide, are often co-located with emissions of biogenic VOCs, including alpha and beta-pinene. As an example, in Appalachia, you have coal mines that are directly located right next to forests. So these emissions are not singularly located. They're very co-located, and they do interact quite a bit. And so to answer this question, up at CSU in Delphine's lab, we have an oxidative flow reactor, also known as a potential aerosol mass chamber, but the community is moving towards calling it an oxidative flow reactor, which is, it's a 13-liter cylindrical chamber made of aluminum. And in our oxidative flow reactor, we mount 2 UV lamps that generate OH radicals. And by changing the intensity of these 2 lamps, we're able to change the amount of OH radicals that we generate in our chamber. And so the residence time in our chamber is about 2 minutes. And because of the lamp intensity in the UV lamps, we can get to oxidation timescales on the order of less than 1 day to all the way up to 20 days if we really want to push it and be a large hit of oxidation. And so what we did is we sent in our alpha-pinene or beta-pinene into our flow reactor, and we oxidized it. We added the equivalent of about 3 days of oxidative aging in the form of OH radicals. And then at the output, we would send our resulting oxidation products for gas phase analysis, which we used high-resolution time-of-flight chemical ionization mass spectrometry. And so again, then we would have our stable oxidation system, or our oxidation system of alpha and beta pinene, and then we would perturb that system with sulfur dioxide. So we would add in that SO2 perturbation and see what happened to the bulk gas phase properties. And so I want to spend a couple minutes talking about high resolution time of flight chemical ionization mass spectrometry. I like thinking about this technique as searching for unknown compounds, unlike a quad SIMS or a spectroscopic technique or even some gas chromatograph techniques, where we're not targeting a certain molecule. We're getting a large suite of molecules. We're sending our total sample from our chamber into our mass spec, and we're getting a whole suite of compounds that then I have to go through and identify by molecular formula what these compounds are. And so to give you an idea of what a spectrum looks like, this is an example spectrum of alpha-pinene plus OH. So on the x-axis here, we have mass to charge and signal on the y-axis, and this blue line right here is our baseline, and any red peak above that, red spike above that, is due to a signal of a molecule that we detect. So we get hundreds of molecules detected across a large mass range above background and above our baseline. And I can tell you that in this suite of compounds, there are about 900 different molecules that I can go through and identify based on molecular formula. So there's a lot of information in here. Because we have a high resolution TOF, time of flight mass spectrometer, we're able to separate and identify these gas phase molecules beyond unit mass. So this is a really, really cool and powerful technique. It's very cool. But of course it comes with its challenges. One being quantification. You can imagine that we can't quantify every one of these molecules that I identify. And we can only quantify what we have standards for or what we can make. A lot of these molecules are carbon, hydrogen, and oxygen combinations that if you made it, it would be explosive. It's just not, quantification is difficult, and that is one of the issues with this technique. And further, as you can imagine, we get a large amount of data. So this is a 1 minute average spectrum. And so we're running these experiments, and we get a ton of data, and it's not uncommon for people to come back from field campaigns with gigabytes of data, and it's difficult to then try to parse that data or understand what you're even looking at when you have so much information. And so one of the ways that we've started to think about this data is to look at and kind of to get past the quantification issue, is to look at qualitative changes, especially for kind of experiments like this in a chamber where we are perturbing our system. So this is a hypothetical experiment in our flow reactor. So we have the time from the start of the experiment and then the signal on the y-axis. These 3 lines right here represent my hypothetical oxidation products of alpha-pinene or beta-pinene plus OH. And so at the start of the experiment, our UV lights in our chamber are not on. We see no oxidation products. we turn on the lights, we add in our either alpha or β-pinene, and we start to see this increase in growth of these oxidation products. Once those stabilize, then we start to perturb that oxidation system with incrementally more amounts of sulfur dioxide. So we start to increase, we add a certain amount of SO2, we let that stabilize, we add a little more, a little more, a little more. And what then we focus on are the changes. So we look at kind of this perturbed system versus the unperturbed oxidized system, and what happens to the total signal due to the perturbation. What happens to certain gas phase species, what happens to the amount of oxygens in each molecule due to the SO2 perturbation. And of course, there are, as I've hopefully convinced you with my example spectrum, there are more than 3 oxidation products. And so how do we then take meaning from that large amount of data in order to condense these changes into significant and real changes that are due to the perturbation? And so I want to introduce the mass defect plot, which is another tool that we use in order to visualize a large amount of data. And so the mass defect is the exact mass of a molecule or of an atom minus its nominal mass. So as an example, carbon has an exact mass of exactly 12. Its nominal mass is 12, and so its mass defect is 0. Oxygen has a mass of, its exact mass is 15.994. Its nominal mass is 16, and so it has a slightly negative 0.006 mass defect. And hydrogen has a slightly positive mass defect. And so we can then kind of put this together. As an example, C10H16O3 is pinonic acid. It's a common oxidation product of both alpha and β-pinene. We can add up the number of carbon, hydrogens, and oxygens in this molecule based on their exact mass. And we get an exact mass of this molecule of 184.1068. If we subtract its nominal mass of 184, we get a mass defect of about 0.1068. And then we can put it on in this mass defect space, we can plot where that mass defect sits as a function of the molecule's mass to charge ratio, 184.1068, and its mass defect. And we can do this for another molecule, C10H14O11, which has a total mass of 310.0432. So that molecule has a mass defect of 0.0432. And we can start to then kind of identify patterns and start to perhaps color these two molecules by their oxygen to carbon ratio, just the number of oxygen atoms to the number of carbon atoms. So pinonic acid has an O to C ratio of 0.3, and a more oxygenated molecule has 11 oxygens to 10 carbons, so an O to C of 1.1. And so we can put all this together to look at patterns in these large data sets. So again, this is alpha-pinene plus OH, a mass defect plot. So mass to charge on the x-axis and mass defect on the y-axis. Each of these points is a molecule that we have detected in our sim, so a gas phase molecule that I've gone through and identified its molecular formula. And you can start, and in the, the color of each point is related to its oxygen to carbon ratio. So you can start to kind of see that species of low mass to charge of low mass have a higher oxygen to carbon ratio, but it's not completely restricted to these low mass to charge ratios. And you can also start to see that, and you might already start to identify that there are patterns in this mass defect plot. And those patterns are actually indicative of functionalization of certain molecules. So molecules that are on this line are different by hydrogen, and so each different point differs by an addition of hydrogen. We can also identify functionalization by addition of carbon atoms, as well as water and as well as oxygen. And so we can start to see kind of these slopes and where functionalization may be occurring as we functionalize with oxygen or water or carbon. We get to higher mass to charges, sometimes lower oxygen to carbon ratios. And maybe we could also look at this in terms of fragmentation. If we lose a carbon, we move this way to lower mass to charge ratios. And so we use these mass defect plots in order to look at our perturbed SO2 system versus our unperturbed system and look at signals that change significantly. So we take our large amount of data. So again, this is Alpha-pinene plus OH, mass to charge ratio on the x-axis and mass defect on the y. And again, each point is a molecule that I've gone through and identified, so it has its own molecular formula. And the colors this time are the amount of change due to the SO2 perturbation. So species that are green to red are all species that increased with the SO2 perturbation, and species that are from green to blue are species that decreased with the perturbation. And so this is interesting. There's clearly a lot of changes going on. But if we think about and we want to look at changes that are significant, we can basically filter our data and only look at species that are significantly above their background or have changed at least by 10%. And when we do that, we still have quite a bit of data, and there's clearly quite a bit of molecules in the gas phase that are changing due to this perturbation. But it's a much more manageable set. We could actually go through and one by one identify each molecule in there and look at its time series if we wanted to, or we could take the whole suite of molecules and look at their total oxygenation, knowing that we've identified or we're looking at those species that have changed the most due to our perturbation. Yeah?
Naive question. Yeah. Why do you look at mass defect? Is it just a convenient way to get out all these molecules of widely different mass on the same plot, or is there something further?
It's a very convenient way to get everything on the same plot. Yep, because you can start to identify patterns pretty quickly in the mass defect plot. Yeah. And so when we applied kind of this mass defect enhancement, or only looking at significant changes because of our perturbation, we do see changes due to the perturbation across the entire spectrum of detected compounds. So this is that same mass defect plot with mass to charge on the x and mass defect on the y. This is for β-pinene plus OH. We let that system stabilize, and then we add in SO2. And so again, each point is an identified molecule in the gas phase, and the size is related to its signal. And the color is, again, that relative change. So the amount that this molecule right here was impacted by the SO2 perturbation. And this is when we added in 10 ppb of SO2 for β-pinene, and we see a similar picture for our alpha-pinene system as well, where we see changes even when adding in not a lot of SO2. And when we add in more SO2, we see more changes due to the addition of SO2. So again, for β-pinene, when we add in 80 ppb of SO2, and also the same for alpha-pinene. And so SO2 is impacting these molecules across the entire spectrum that we detect with the SIMS, as well as across different sulfur dioxide concentrations. And what we decided to do is we were looking at these plots, and your eye is kind of drawn in some way to, well, there's more red points in alpha-pinene or β-pinene, or can we quantify these changes? And so what we did is we took basically all of the relative changes that we calculated for each molecule, and we just added them up. And when we did that, so on the x-axis here, I have the amount of sulfur dioxide that we added, ranging from 5 parts per billion all the way up to 80. And then on the y-axis is just the total amount of change. So just adding up all those colors in that color bar. How much did stuff change due to the perturbation? The blue points right here are the alpha-pinene system, and the red are the beta-pinene. And so you can see that as we start to increase the amount of SO2 that we added, we see this shift in this distinction in between alpha and beta-pinene oxidation systems. So not only do we see more changes, so our eye was right, we see more changes when we add in more SO2, we see that the SO2 perturbation is affecting alpha and beta-pinene differently. We also did a few experiments in our chamber at higher relative humidities to kind of test if this held in other environments. And that is shown in the alpha-pinene is the cyan, and the beta-pinene is the magenta colors. And we see that same effect where as we increase the amount of sulfur dioxide added, we see more changes to the system. It's just a slightly dampened system. We don't see as much as in the lower relative humidity system. So we see changes due to SO2, and it's clearly affecting the chemistry of these oxidation systems of alpha and beta-pinene. then we wanted to know how, like, what actually is SO2 doing to the chemistry of these systems. And so to do that, we applied what we've learned about aerosols to the gas phase, and we started to think about putting our gas phase data in traditional aerosol frameworks. And so this is a Van Crevlin plot that I'll be showing quite a few of these plots, with the oxygen to carbon ratio of a molecule on the x-axis and the hydrogen to carbon ratio on the y-axis. And so I like this plot because this is showing photochemically aged organic aerosol. So this is all aerosol data that starts with the primary emissions up here that are very low oxygenation. And then as we start to oxidize them, they functionalize and they move down this pathway to higher amounts of oxygen in the particle. And we can also think about the amount of, or think about how these species are functionalizing by applying slopes from our starting material to where we end up and seeing what that slope is, because that can tell us something about the chemistry. So a slope of 0 would tell us that from our starting material to our ending material would tell us that we're adding alcohols or peroxides. A slope of -1 would tell us that we're likely functionalizing by adding carboxylic acids. And so we can use this slope analysis and Van Crevlin diagrams in order and apply those to our bulk gas phase O to C and H to C ratios. And so I went through and I calculated for each alpha and beta pinene system, and then how with the SO2 perturbation I can calculate a total O to C ratio and a total H to C ratio. And then we can think about where we, of both alpha and beta pinene, and we can think about where we started, which is at an H to C ratio for our monoterpene of 1.6 and an O to C of 0. And so when we oxidize both our alpha and beta pinene, we see that things are, they're sitting near the 0 slope line, which is actually good because we are adding OH, so that's good. That's indicative of that chemistry. But we can also look at how the SO2 perturbation changes where the bulk O to C and H to C ratios sit for these species. And I also want to point out that these points right here that are outlined by the blue circle are correspond to alpha-pinene, and the red correspond to beta-pinene. And they were definitely distinct in terms of, we oxidized both alpha and beta pinene, and we got a distinct oxygenation amount for each of them, which is actually really interesting. And so when we do our slope analysis, we start at that H to C of 1.6 and O to C of 0. As a function of added SO2 on the x-axis, we do see that the addition of SO2 affects the oxidation mechanism. So if we start at 0, where we're not adding any SO2, this is just alpha-pinene and beta-pinene plus OH, we see our slope similar to 0. It's slightly negative. But then as we add SO2, we start to decrease that slope. And so we start to change either the oxidation mechanism or the oxidant of these alpha and beta pinene oxidation systems with the addition of SO2. And we see that same pattern also for our experiments that we did at higher relative humidities. It's just a little, again, slightly dampened. But we thought it was really interesting that not only did sulfur dioxide change, or it impacted the total systems in terms of our total, it impacted individual molecules, it impacted the total systems, and it also somehow affects the oxidation mechanism and or the oxidant of these oxidation systems. And so now I want to quickly switch gears. This was with a biogenic, somewhat simplified system. We were only looking at 2 molecules, alpha-pinene, beta-pinene, send them into our chamber, oxidize, and see what happens when we perturb the system. I want to switch gears a little bit and talk about a more complex system, which is diesel engine exhaust. So about a year ago, CSU has an engines lab a few blocks away from the chemistry department. So we took a couple instruments down to the CSU engines lab where we wanted to study the secondary gases and particles from diesel engine exhaust. So again, In this case, our perturbation is the amount of oxidation that we were exposing our primary gases and particles to. And we were again trying to look at the interactions between the gas phase and the particle phase as a function of oxidation. And so we had a very similar setup for this kind of more complex system where we took a running engine, so more complex species were emitting gases and particles, and we sent those emissions into our oxidative flow reactor with our same UV lamp system, so we're still generating OH radicals, and we still are able to generate quite a bit of OH radicals. And in this case, this is a little more representative of near-field aging, I would say, of about a couple hours to a total of about 20 hours of oxidative aging. So stuff comes out of your tailpipe, and then what happens to it as it's exposed to oxidants in the atmosphere. We also looked at two different fuel types. So we had our engine employed either biodiesel or diesel fuel, and we also looked at two different engine conditions. Either the engine was idling or it was at load conditions, at about 50% load conditions, so actively running. And then we also sent our secondary species after oxidation. We sent them to gas phase analysis with our same high resolution time of flight chemical ionization mass spec, as well as particle phase analysis where I was running a high resolution aerosol mass spectrometer. And again, our perturbation in this case was just adding in more and more of OH. And so when we look at how these experiments worked and what they looked like, we found very quickly that a diesel engine plus OH gives you more and more organic aerosol as you increase the amount of OH that you are generating. And so here, this is on the x-axis just the time since the start of the experiment. And on the y-axis, I'm plotting the organic aerosol mass from the AMS. And there are two traces on here. This green line is when the engine is idling, and the black dashed line is when the engine is at 50% load. And so at time 0 for the first 20 minutes, these are just indicative of our primary emissions. So we're not turning on the lights in our chamber. We're just looking only at the primary emissions of aerosol right now. And then as we start to slowly turn on the lights and increase the amount of OH that our primary gases and particles are exposed to, we see this increase in organic aerosol for both the idle and the 50% load. And so again, we can change the amount of OH that we're exposing our primary emissions to by changing that lamp voltage in our chamber. Again, it was about an hour to a total of, on maximum, about 20 hours of oxidative aging. And another thing to point out that I'll come back to is that the idle and the 50% load clearly have different amounts of aerosol, of organic aerosol generated. And this is actually a very interesting result that I will come back to. But and so I want to start by, this is that same Van Crevelen diagram with H to C, our H to C ratio on the Y and our O to C on the X-axis. And so I want to start with putting just what we observed from the aerosol phase on here. So these are all particle phase data where the diesel idle are here in the circles. They're filled if they're in idle. The biodiesel idle are in the triangles that are filled, and the load for both the biodiesel and diesel are in the unfilled symbols. And the main point here is that we start at a high H to C ratio as we add in more and more oxidation, which is represented by the color bar, the color bar is indicative of the amount of voltage that we applied to our lamps to generate more and more OH radicals. So from about a couple hours to all the way up to about 20 hours of equivalent oxidative aging. So as we oxidize our particles, we start to functionalize. We get to more oxygenated particles. We start up here at high H to C, and then we add oxidation, and we slowly move this way towards a more oxygenated aerosol fraction. If we put the gas phase on here as well, we see a similar pattern where we start at an H to C that's much higher, and then as we oxidize our gas phase, we move in the same direction. Another thing to point out is that, and this is another kind of interesting very applicable result is that the fuel types actually were quite similar. Our biodiesel and diesel fuel behaved pretty much the same, but our engine loads differed in their amount of aerosol production. And so an indication that it kind of matters how you drive your car in terms of secondary chemistry. Yeah.
So are these heavy-duty diesels or car
Heavy duty, non-road.
And is this before emission control?
This is a tier 3 engine, so there are no emission controls. I have a note about emission controls that I can tell you about. That's pretty interesting, actually. And so again, the particles and gases in this Van Crevelen space look like they follow each other. But I can hopefully convince you of that instead of just looking at this mathematically by doing that same sort of slope analysis to see how the functionalization of both the gases and particles is occurring with oxidation. And when I do that, so again, lamp voltage on the x-axis, which is just indicative of increasing atmospheric age, and the slope from that starting primary material to that ending secondary material as a function of oxidation. For both the gas and the aerosol, so the gases are these circles and the particles are in the triangles. And then for diesel fuel and diesel in blue and biodiesel in red, both the gases and particles definitely seem to move in the same direction at the highest amount of oxidative aging towards functionalization by carboxylic acids. And so while the oxidation slopes suggest that the chemistry is the same for both the gases and the aerosols, the aerosol production, as I mentioned before, of the different engine loads is different. It's significantly different. So again, increasing atmospheric age on the x-axis and what I call the organic aerosol mass enhancement on the y-axis, which is just the amount of secondary organic aerosol formed as compared to the primary organic aerosol. As we increase the amount of oxidation in our chamber, we see an increase in organic aerosol mass. These circles are the biodiesel and diesel idle experiments, while the triangles are the diesel and biodiesel load experiments. So there's a real significant difference in between, again, the engine loads as compared to the fuel types. And so again, we're going to apply what we've learned about aerosols over the past decade, 2 decades, in order to understand and look at the gas phase in order to try and understand where these differences in aerosol yields are coming from. And one way to do that is by looking at the saturation vapor pressure, or C star, or volatility of a species, as well as its oxygen to carbon ratio. And so we can start to track where our gas phase species are based on if they move in a certain direction on this plot that may be indicated in an indication of fragmentation or functionalization, etc. And so we can actually take all of our gas phase data, use a simple model in order to calculate our C-star saturation vapor pressures based on the molecular formula of each molecule. And so as a quick example of what these plots kind of look like. So again, I'm showing the C-star saturation vapor pressure on the x-axis, also increasing volatility this way, and then the oxygen to carbon ratio on the y-axis. And I plotted here just some commonly observed molecules in the atmosphere to give you an idea of where things move around in this plot. And everything is colored by the oxidation state of that particular molecule, which is related to the O to C ratio. And so we can see the species that are over here in this side of the plot are very high volatile species. They will exist mainly in the gas phase. As we move towards lower and lower volatility species, we get to molecules that are likely to contribute to the total particle mass in the atmosphere. And again, we can also kind of use what we've learned about categories of these volatility compounds in the atmosphere in terms of where do the volatile organic compounds sit, where do the species of intermediate volatility sit, semi-volatile, low volatility, and extremely low volatility, in order to think about where our data sits and where our data fits in and how the gas phase is possibly contributing to the particle phase. And so again, this is that same plot with increasing volatility or saturation vapor pressure on the x-axis and oxygen to carbon ratio on the y. This is all gas phase data, so this is all from the SIMS, where each point is again a molecule that has been identified, has its own molecular formula. The size of the point is related to the amount of change in terms of how much the oxidation affected the signal of that species as compared to the primary emissions. And again, it's colored by oxidation state. And so after about 3 hours of aging, we see quite a few species kind of all throughout a wide volatility range. After about 12 hours of aging, we see that there's just more stuff. More stuff in the gas phase has grown in as compared to the primary emissions. And really, to me, this indicates that there's just more condensable material that is measured with increased aging. There's just more stuff that's able to then partition to the particle phase. And again, so this is that same plot, and this was for an idle experiment, an idle biodiesel experiment. That's that same plot after about 12 hours of aging. And if we compare that to what we get with the load experiments, we see just a lot less stuff. And so there seems to be more condensable material measured in the idle experiments. And if we put this together in terms of our aerosol, the differences in our aerosol loads, the gas phase is potentially explaining what's going on in the particle phase and why we see these distinct differences between the idle experiments and the load experiments. There's just more material in the idle as compared to the load that's able to condense or contribute to the total particle growth in this experiment. And so again, we can to all of our data, we can kind of try to condense it a little bit more, and we can apply what we know about the volatility categories in the atmosphere, and put it all together on its own Van Crevlin plot. So again, oxygen to carbon ratio and hydrogen to carbon ratio on the y-axis. So here, this is our bulk particle phase for a biodiesel idle experiment. So we start up here with our primary emissions of very low oxygenation, and then we functionalize as we add oxidation. And the gas phase looks very similar as well with increased oxidation. If we then calculate just what our semi-volatile organic species are doing, we see that, so this point right here is representative of our primary semi-volatile SVOC emissions. And then as we age and get to about 20 hours of aging, we functionalize our SVOC. And we see the same thing for our LVOC, for our extremely low volatile organic compounds, and to a lesser extent for our intermediate volatility. And what's also interesting is that our volatile organic species that we measure are kind of off doing their own thing. And this is as we start with our primary emissions and then we age them after about 20 hours. This is indicative of fragmentation. And so the species in the gas phase that are likely contributing to the total particle mass, in this Van Crevlin space, they look like the particle phase, whereas the VOCs that are likely not contributing at all to the total particle mass, they're kind of off, they're fragmenting away, they're going towards CO2. And so I think this is a really actually interesting way to understand and to look at what's actually happening in the gas phase and how the gas phase has been contributing to the total particle mass. And so quickly, I want to summarize that sulfur dioxide additions impact the secondary chemistry of alpha and beta-pinene, and an interesting note is that they impact them differently. The gas and particle phase do behave similarly with increased exposure to OH oxidation. And this is kind of not a very exciting point, but it's actually really interesting that the secondary chemistry is a function of how you drive your car. The fuel types didn't actually make a difference. And so I think in our changing kind of energy and and thinking about using biodiesel fuels as a more environmental friendly fuel, and in terms of the secondary chemistry as well as the primary emissions, it didn't really matter. And then also, I think it's an important note I'm sorry. I think it's an important note to think about applying and continuing to apply all the things that we know about aerosols, that we've done so much work on these aerosol frameworks, and applying them to the gas phase and putting everything together on one plot in order to understand how these interactions between the gas and particle phase are driving the total organic aerosol mass in the atmosphere. And then I also want to take a quick couple minutes to talk a little bit about kind of my current and future work that has really been driven by what I've talked about today. So I briefly mentioned that alpha-pinene and beta-pinene, when I oxidized them in our chamber, they exhibited distinct bulk gas phase oxidation properties. So the total amount of oxygenation for alpha-pinene was different than beta-pinene. And I've done these a lot, and it doesn't seem to change. There's still that difference. And we started to wonder if that difference was then indicative of differences in aerosol yields, because some alpha-pinene and an example, alpha-pinene and NO3 forms no aerosol as compared to beta-pinene plus NO3. So we started, and of course this is for OH oxidation, but we started to think about maybe what's happening in the gas phase could tell us more about these differences in particle yields. And our hypothesis is really that it's all due to the structural differences between alpha and beta-pinene. And so what I've been currently working on is doing more and more chamber experiments of different pairs of structural isomers that are similar to alpha and beta-pinene, and seeing how that impacts the total particle yields. If we add in more OH, or if we do example ozone or NO3 oxidation, how does that impact kind of this bulk gas phase oxidation state? And if we use particles, does that impact? What about the seed? If we use acidic seed or such, does that impact the total, or does that impact the organic aerosol mass or the bulk gas phase oxidation? And that brings me to the other big question that I've been thinking about, is then relating kind of what's happening in the gas phase, because I think they are very, very interconnected. So relating what's happening in the gas phase to what we're measuring in the aerosol phase. So this is a rather raw plot, but I think it illustrates nicely what I've been thinking about. So on the x-axis here is the gas phase oxygen to carbon ratio for the engine experiments. So this was both diesel and biodiesel engine exhaust oxidized at a range of oxidation, or for a whole span of oxidation timescales. And on the y-axis is the amount of organic aerosol that was formed relative to the primary organic aerosol. And it seems to be that there is definitely some relationship between this bulk gas phase parameter as well as the organic aerosol. And so again, I've also been thinking about, can we put, a biogenic system on here? Where does that sit? Do they sit together? Are there differences in environments, kind of building up kind of a gas phase and a particle phase metric and parameterization that may be useful in terms of, if you go somewhere and you're in the atmosphere, you're in the ambient atmosphere, and you measure a certain, if you measure gas phase compounds, can we translate that to what's happening in the aerosol phase? And with that, I will thank you for your attention, and any questions? Thanks. Okay.
So I guess we should use the mic for questions, but I'll open it up to anybody.
Yeah.
So it's about your summary slide and the third conclusion. Yeah. So is this really, the study, is this applicable to passenger vehicles?
That's a good question. I think so, based on what other people have done at the engines lab.
But they would have emissions controls.
Definitely. But we also, I will say that we did some emission controls also. We did some experiments, and those really have an impact only on the primary emissions. As you oxidize, the secondary, like the amount of aerosol that you form, even with the emission controls, is as much as the idle, is as much as without the emission controls. So that is definitely an open question. But I know they're developing, I think we're going to go back and do some more with some of the more recent technology.
So then the other question is, why do you think you have such different curves between an engine under load and the idle engine?
They actually, it has to do with their emissions are different, essentially. So what you emit from a vehicle at load, it's a lot more, you get to almost more complete combustion.
So is the combustion temperature higher in the
I believe I've looked at this.
Because with a diesel, right,
Mm-hmm.
the volume at which it explodes is
Mm-hmm.
the same.
Mm-hmm.
Under load and not under
Mm-hmm.
because it's not compression,
Mm-hmm.
it's flow.
Mm-hmm.
So the volume in the cylinder is the same.
So I believe that the temperatures are different, but I'd have to go back and look specifically. Boy. Yeah.
So the technology exists already to just turn your car off when you're at a stoplight.
Mm-hmm.
So are you saying we should just, all the cars?
I've thought about this, like when you probably deal with this here, like when I'm in Fort Collins and there's a train, you know. This is like what now I think about when I'm waiting for the train, and I sit there idling and I think about the emissions coming out of my car. I mean, it can't hurt, but then there's also like, we didn't do any experiments in terms of the startup, because that could be even more. So I don't know how much that compares in terms of starting up your car versus just letting it run, and that's an interesting question.
So,
Yeah.
We saw studies last week which showed that startup emissions out of diesels are much higher than miles.
Okay. That's interesting.
Quick question. How much OH did you typically have in the flow reactor?
It's about on the order of 10 to the 11 to 10 to the 12. Yeah, it's a lot.
I guess SO2 would react with OH to make HO2.
Mm-hmm.
I wonder if CO would behave similarly to convert OH to HO2.
That's a good question. That's definitely a good question. We've thought about other perturbations because we definitely didn't. Yeah, that's another. Yeah, definitely.
A couple of questions down here.
So with respect to your first conclusion there, what would be the takeaway message if I'm interested in comparing an environment, say in this country, maybe to, say, somewhere in Asia where SO2 emissions are very much higher, but I've still got a very, maybe depending on the region. I know we've just had a field campaign in Korea. There was a lot of pinene there, but high SO2 as well. So with respect to that, you know, the SO2 additions affect the secondary organic chemistry differently with respect to eventual SOE, AE concentrations and things like that. How do I expect these environments to differ?
That's a good question. So I want to point out that we did a range from about 5 to 80 ppb of SO2, and I think the 8-hour average for the EPA standard in the US is about 75 ppb of SO2, and I imagine in China or Korea it's a lot more. And so then I think actually SO2 could actually start to compete with other oxidants, maybe if there's enough of it, depending on certain reaction rates, et cetera. But I think that where this is most important is where there's like a point source of SO2 right next to a large amount of emissions of alpha and beta-pinene. And so that could be important. I don't know if then that will flush out in terms of I don't know if you'll be able to see it in the impacts of kind of what the organic aerosol is doing in Korea or China. But I can imagine that on a smaller, kind of on a regional level, it might actually have an impact on some of these emissions.
Hi, Beth. Thanks. So I had a question. You show that there was some VOC formation in some of your experiments, and one thing that I'm really interested in is how does maybe absorbing aerosols, if you have them and you have these 254 nanometer lights, are they absorbing, and then maybe some of the fragmentation or chemistry that you're seeing, is due to that. And I know in the PAM and the gas phase, if you control it correctly, you're OH dominated in the gas phase. But I'm also curious if there's something maybe happening in the particle phase, because that would be very interesting too.
So I can tell you that for the alpha and beta pinene experiments, we didn't see particles, but our measurement wasn't greater than 60 nanometers. So I'm sure there were particles in there, because, yeah. So and we've just started to do more seeding experiments in the PAM, and at least on the particle side, when we hit a bunch of particles, at least ammonium sulfate or ammonium nitrate with a lot of OH, we don't see changes in the particles. But that doesn't necessarily mean that stuff isn't happening. So that's a really good question, and it's something that we actually need to consider when we're putting in particles or we're making particles and such.
Yeah, I just think it'd be really interesting as like as an additional piece to figuring out if particle phase reactions are helping to drive what you see a little bit in the gas phase as well.
Yeah. If it goes both ways, kind of that arrow goes. Yeah, definitely. Yeah.
Yeah, nice talk, Beth. So do you have NOx present in your flow tube?
No.
No. But presumably the diesel has some NOx because of their combustion?
It has a lot of NOx.
A lot of NOx. So I'm just wondering if you could speculate on how the slope of the VK plot would change with NOx.
That's a great question, and that's something that we wanted to go back to on a more simplified level, because we didn't necessarily expect we knew there would be NOx, but we didn't realize how much NOx would come out of that engine. And that especially impacts, in our chamber studies as well, it impacts the amount of OH exposure as well. And so that comes with some funny things. But I would guess that it would impact the functionalization, and maybe, I think the gases and particles would still continue to behave the same, but maybe we would go towards more oxygenation, or maybe towards more additions of kind of more carboxylic acids or something like that. But that's definitely something that we want to go back to on a more, like, even just the alpha and beta pinene, it's on the to-do list to do NOx also, and say, like, well, is this the same effect for something that's a little more reactive?
Thanks for a nice talk. I think it's cool to see all these sort of emergent properties coming out of this, soup of chemicals, but I'm wondering if you've, started comparing those to models, and if you already know the models would do poorly in certain ways.
Not to a large extent. I've started looking a little bit at particle yields of different monoterpenes, kind of in thinking about how those differ and how they differ in experimental versus the actual model. But I don't know if I can fully answer that without a little more time. And I don't. One thing too to point out that I didn't really emphasize is that the fact that alpha and beta pinene are different is actually really interesting to me, because I think a lot of models base some of their oxidation chemistry on just alpha-pinene, and I'm not sure if that's a way to go forward, or if we should start thinking about more of the structure of monoterpenes, or is alpha-pinene just weird in its own anomaly and maybe everything else is totally similar. And so that's one thing to start thinking about and to start looking at.
So I think we better wrap up there. Let's thank Beth again for an interesting talk.